Today, we're going to start looking at partial derivatives. So we have here a table representing a function of two variables. So this is going to be some surface in R3. So I've got my function of two variables. P is a function of T and C, where T is apparently time in months, and C is some kind of concentration in parts per million. And the values in the table are percentages. So this represents the percentage of rats surviving after T months, a concentration of C parts per million for some apparently toxic substance. So if we think back to our original big questions in calculus, one of them was to find the slope of the line tangent to a curve at a given point. And that would tell us the rate of change of that function with respect to the variable. Here we have two variables, so we're going to want to find two different rates of change. And those are going to be our partial derivatives. All right, let's first look at this table and read what the table is about. So this represents the percentage of rats surviving, concentration of C parts per million of some substance after T months. So if we pick this number here, this 93. So one of the values of our function, we could say that's f of 18,6 is 93. So what this means is that 93% of the rats are still alive after 18 months after being exposed to a concentration of 6 parts per million. So this says 93% of rats are still alive (18 months) after an exposure of 6 parts per million. That's just how we interpret the values in the table. Looks like f of 24,0 is 95. 95% of the rats are still alive 24 months after an exposure of 0 parts per million. So we can see kind of what we expect. We can see that we have a decreasing function of time, because over time we should expect fewer rats to survive. Also, we can see a decreasing function in terms of concentration. So at a given time, we see a decreasing function with respect to the concentration. Increasing the concentration seems to decrease the survivability. So we kind of have a sense of what's going on in this function. We can also notice that this is not, it looks like we don't have a linear function. Our rate of change is not constant. Now, when we say that, we have to think about two different rates of change. We have a rate of change of the percentage with respect to time, and a rate of change of the percentage with respect to the concentration. So we have two rates of change. So notice that if I pick a fixed value, of time, my decrease is not, the amount of decrease is not constant. So at a fixed time of t equals 20 months, I'll pick 18, at a fixed time of 18 months, we go from 198, and then from 98 to 93, and then from 93 to 82. But then we have to look at how things are changing. It goes from 0 to 2, that's an increase of 2, and then from 2 to 6 is an increase of 4, then from 6 to 15 is an increase of 9 in concentration. So let's just pull out this fixed 18 months and see what we're looking at. Let's look at this column right here. Let's look at this when t equals 18. So for a fixed value of t equals 18, let's make the function of concentration. Let's look at the percentage as a function of concentration. So I'm going to have concentration in parts per million. And here's going to be the percent survival, P, and this is going to be in percent. So at a concentration of 0, after 18 months, we have 100% survival. At a concentration of 2 parts per million, 98%. At a concentration of 6, we're to 93. And then at a concentration of 15, we're at 82. So if we just look at this fixed value of t equals 18, we can look at how the percent changes with respect to the concentration in the same way that we always done. Look at the change dp or delta p over delta c. So here we have a decrease of 2 when C increases by 2. So at 100, or at 0 concentration, it looks like we're decreasing by, the rate of change is -2 over 2. Then from 2 to 6, from a concentration of 2 to 6, we go from 98 to 93%. So that's a decrease of 5 over an increase of 4. And then finally, from 93 to 82, that's a decrease of 9, 11 over an increase of 9. So it looks like at 100, we can approximate the change in P over the change in C is -2 over 2, or -1% per part per million. Which is a great unit. A percent per parts per million. We should probably simplify all those pers out of there. So this is at a concentration of 0. But then at a concentration of 2, coming into 2, we have a decrease of 1% per part per million. And then, but from 2 to 6, if we recalculate the slope, it looks like the change in percent divided by the change in concentration is going to be -5 percentage points over a 4 parts per million. And then we can also calculate from 6 to 15. So from 6 to 15, the rate of change, the change in P will be 11, -11. over an increase of 9 parts per million. So 11 divided by 9 is going to be 1.2. Yeah, 11 minus 9 is 2, so 1.2. So here we're looking at the rate of change of the percentage with respect to the concentration for a fixed value of time. So we're looking at the rate of change of the percentage with respect to concentration for a fixed value of time. So we're holding time constant, and we're looking at how concentration affects the percentage. If we shift over to a different column, we can look again at the rate of change of the percent with respect to concentration for another fixed value of time. So for, let's say, t equals 20, we'll have a different function. So when t is equal to 20, our function will have a c in parts per million and a p in percentage. But for t equals 20, we have a different set of values. We go from 99 to 97, 97, so 99, 97, 90, and 70. So for the same concentration, 0, 2, 6, and 15, we go from 99 to 97 to 90 to 70. So once again, we're looking at the rate of change of the percentage with respect to the concentration. And so we'll have units of dp, delta P over delta C as percent per part per million. We can also do the same thing in the other direction. We can choose a fixed concentration and look at how time affects the percentage. So earlier we had looked at f of 18 and 6 is 93. So we could look at a horizontal row of the table. And for a fixed concentration, we can look at how time affects the percentage. So for a fixed value of the concentration, we can also run out of space on our paper. That's great. So we can make a table of values for c equals 6 and think about a one value problem or a one variable function. So I'm going to have time in months and down here percentage in percentage. And so the time goes 14, 16, 18 divided by 2, 14, 16, 18, 20, 22, and 24. And our percentage on that row is 96, 95, 93. Uh, 90, 86, 80. So now we're calculating another rate of change. We can calculate dP over dt, the rate of change of the percentage with respect to time for a fixed concentration. So in the previous, when we were looking at, in the previous question, we were looking at the rate of change of the percentage with respect to concentration. How does concentration affect the percentage of surviving rats at a fixed point in time? And now we're analyzing the other direction. How does time affect survivability of rats for a fixed concentration? And so here we'll be calculating dP over dt. And if I just do the first one here, we'll decrease by 1% in 2 months. I should have been less lazy and not written percent per month, percentage points. And then once again, we can calculate all the different values of dP, dt. And we have the units of percentage points per month. So what we want to note, we had a function of 2 variables. So now we have 2 rates of change, but the way we interpret the rates of change is the same way that we interpreted rate of change way back when we started learning about slope. Since slope is delta y over delta x, the units of slope are the units of y per units of x. We are doing the same thing here. So interpreting the rates of change is just interpreting slope, and it works the same way we did before. Same way it did before. So if the slope is delta y over delta x, then the units of slope are the units of y. Then you write per, and then you write the units of x. So interpreting things works the same way. We just have to interpret in 2 different directions. In the 1 variable problem, we wanted to find the equation of a line tangent to a curve at a given point. In the 2 variable problem, we'll want to find the equation of a plane tangent to a surface at a given point. Our curve became a surface, so our line became a plane. And both of these represent a linear approximation of the function. So in both cases, we're looking for a linear approximation of the function. So we in the one, if we have a function of one variable, we want to find the line tangent to the curve at a given point. If we have a function of two variables, we're looking for the equation of a plane tangent to a surface at a given point. The given point in the equation of the line is just say at x equals x naught. But a given point on a surface will have two inputs, x naught and y naught. Or better yet, I could say that the given point is x naught, y naught. Yeah, no, I don't want to do that. These are just the inputs. We plug in one value of x for the equation of the line, or we plug in a value of x and a value of y to find the equation of the plane. The equation of the line tangent to the curve at a given point. I didn't leave space. In my mind, I'm like, oh, leave space so you can write the equation. And then when I wrote it, I'm like, oh, nah. See, if you had a professional teacher, things like this wouldn't happen, but you got me, so I don't know. So with the equation of the line tangent to a curve at a given point, we write y equals, we plug in the value of the function, so f at x naught. And then we'll write the slope is f prime evaluated at x naught times x minus x naught. So here's the point slope equation. This is the line that goes to the point x naught, f at x naught, and has slope f prime at x naught. Here's what we need to adjust. That f prime at x naught, when we have a function of two variables, f prime doesn't really mean what we want it to mean. F prime is the derivative of y with respect to x at x naught. So this is how y is changing in the x direction. Oh, I guess it's a derivative, so it can be dy dx, how y is changing with respect to x. So for the equation of the plane tangent to a surface at a given point, z is going to have to start off by evaluating the function at the point, so f of x naught, y naught. We'll need some slope in the x direction and another slope in the y direction. The coefficient of x is going to be how z is changing with respect to x. And the coefficient of y will be how z is changing with respect to y. These rates of change are going to be partial derivatives. So rather than dy and dx, we use a different looking d, but we still say dz dx. So these are going to be partial derivatives. Partial derivative of z with respect to x. And we use the funny looking d for partial derivatives. We look at how z is changing with respect to x if y is constant, or how z is changing with respect to y when x is constant. So dz dx is going to be how z changes with respect to x when y is constant. Dz dy will be how z changes with respect to y when x is constant. So here's how we're going to modify our Leibniz notation. We're going to have to modify our Newton notation, the prime notation. And we're going to use subscripts for that. So the partial derivative of f with respect to x, I'm just going to write, with not enough space, a subscript, fx evaluated at x naught, y naught. So I'm going to say fx at x naught, y naught, when I mean the partial derivative of z with respect to x at x naught, y naught, and fy. We should be saying f sub y, but we're not gonna. We're just gonna say fy and fx. All we're doing is modifying the thing that we had before. Our line was a starting point and a direction. Our plane is a starting point and two directions. That makes sense. We go from a one-dimensional line, we only need one number to describe the direction, to a two-dimensional plane where we need two numbers to describe the direction. So in that sense, this is very satisfying the way this works. If we go from R2 to R3 up to R4, then our function of three variables will be a solid tangent to a solid at a given point. So it's hard to picture now because we've got four variables running around. We're in R4, but mechanically, we can see how it's flat. We have a starting point, f of x naught, y naught, z naught. And there'll be an fx at x naught, y naught, z naught times x minus x naught. And fy at x naught, y naught, z naught at y minus y naught. And an fz, it'll be just tack on another term. Fz at x naught, y naught, z naught times z minus z naught. So if by the first one you mean f prime at x naught, when there's only one variable, we can say the first derivative we can just indicate that with a prime. It says take the derivative. But when we have a function of two variables, when there's a function of two variables, we can't just say take the derivative. That raises the question, what derivative? The derivative in the x direction or the derivative in the y direction? So we need a way to distinguish the two. So we can't just say f prime at x naught, y naught. There are going to be two derivatives, two partial derivatives. So we do that with a subscript. Fx is the derivative with respect to x, and fy will be the derivative with respect to y. Any questions? How's everybody okay? The main thing that we want to get from this when we're talking about is that we're thinking about linear approximations of functions. This is how we always like to imagine things. Our default mode of thinking is to think linearly. That's always the default mode of thinking. So if we're negotiating for the price of a thing, and I'm at 2,000 and you're at 3,000, we'll sometimes we'll say, let's split the difference. That is, let's agree to think linearly and just connect a line between 2,000 and 3,000 and land at 2,500. But there might be an alternate universe out there where splitting the difference means instead of making a line between the two, maybe we think instead we'll just multiply the two and then take the square root. So like let's split the difference with a multiplication. So we'll do 2,000 times 3,000, take the square root, and end up at 24. Just go with 2,400. I'll do two significant figures. So this is what, when we think about linear functions, we don't just want to think geometrically about linear functions, a line or a plane. We want to think about linear functions in terms of equations, because we want to see this set of symbols and think line, and then see this set of symbols and think plane. We want to picture these things and say these are flat objects. The reason we want to do that is that when things go past 3 dimensions, when we have a four-dimensional object, we can still see a linear function, and we still interpret that as flat. We can still see that constant rate of change in any direction. Any questions? How's everybody okay? Everybody's blurry. How's everybody okay? If you're thinking, I'm a little bit shaky on what's going on here, I don't totally understand, then that is the correct answer. It's the first day we started talking about partial derivatives. I barely said partial derivatives. I haven't told you how to calculate anything. I haven't said this is what you do in this particular moment. I've just tried to connect what we're doing now with stuff that we've done before. So if you're not sure where this is headed, that is the correct answer, but you can find out by reading along and starting to do some problems. As usual, I recommend starting to do some problems without reading the section. Don't read the math book, then do the problems. Just start doing the problems and then use the math book to look at examples that compare to the problems that you're dealing with. Any questions? Comments? Deep thoughts? All right, that's going to do it for today. I'm going to open up some homework from chapter 14. Chapter 14 is going to take way more than a week. I know we did chapter 12, all the homework was in a week. Chapter 13, all the homework was in a week. But chapter 14 is more new stuff that we're trying to draw together. And it's going to rely a bit on chapter 12 and chapter 13. So while we're learning chapter 14 stuff, we are also reinforcing chapter 12 and 13. So that's going to do it for today. As soon as they appear, get started on the chapter 14 homework. I'll see you all tomorrow. Everybody have a good day, and thanks for playing.